Okay, this is the third hour of Physics 1C for September 1st. We have a little bit less than an hour, but we're going to get through a couple more problems here. One of the students had asked about this problem, which is from the textbook. It's not a problem, it's a question. And so I thought we'd read it together and have everybody try to think about it themselves. So it says you have two lightweight metal spheres, each hanging from an insulating nylon thread. It says one of the spheres has a net negative charge, while the other sphere has no net charge. It says if the spheres are brought close together but do not touch, will they attract each other, repel each other, exert no force on each other? And then B says you now allow the spheres to touch. Once they have touched, will the two spheres attract each other, repel each other, or exert no force on each other? Okay. I don't know if I've said enough in today's class that you can answer this, but it's possible. I mean, I have said some things that you need to know to answer this question. So let's see how you all do. Let's take it one at a time. So let's just start with A, okay? So everyone read it yourself. Okay? It is tricky. No, Kavi, it's tricky for sure. I want everyone to read this question. Just read part A. I can draw a picture too. What do we have? Two spheres. In part A, what we have is a sphere here. We have a sphere here. One of them is what? Negative? Yeah, this one's negative. This one's neutral. Right? And the question in part A says, if they are brought close together but do not touch, will they 1 attract, 2 repel, 3 exert no force? I want you to put your answer in the chat. Do you think it's going to be 1 they attract, 2 they repel, or 3 they exert no force? Just put your answer in the chat. Everybody do it. Doesn't matter. Just yeah, you can write your answer in words too if you prefer. Okay, I've seen a lot of 3s and 1s. So people think that they will either attract or, and by the way, it does say that they are metal spheres, and this matters. They are metal spheres, conductors, hanging from an insulating thread. So the thread is an insulator, right? So I don't know for sure, but I'm reasonably certain that the answer in this case is 3. Which is what it seemed like a lot of people, but people either thought that they were going to attract or repel. They definitely will not repel. Everyone thought that they would either, attract or exert no force. It's good to see nobody thought they would repel. That's really smart. Those of you that thought they would attract each other, though, were you thinking that maybe what would happen is that this would induce polarization inside of this object right here, and as a result would cause them to be attracted to each other? See, it might.
Yeah, I was thinking similar to the example that you showed us with the balloons.
With the balloon, like the wall and the balloon, yeah.
Yeah.
The problem is that the wall and the balloon are both insulators, right? And these are both conductors. So let me make this bigger so we can talk about this. I'm really glad you asked this question, Kavi, by the way. I appreciate that. So if this is in fact negative, and you bring a neutral sphere near to it, it's definitely the case that because this is a conductor, little negative charges are going to go to this side, right? And this side will become locally positively charged. Now, I guess the question is, do you all agree that this is what's going to happen inside of the ball? Remember that if it's a conductor, the charges are free to move, so the negative charges should run to the right side, right? And this side should become positively charged. Now, the question is, will it be enough to attract the objects? And maybe it would. I don't really know what the answer to this question is, to be honest. And that feels good. I like not knowing. That's exciting. I would have chosen 3. Because they say if they're brought close together but do not touch, polarization probably will occur. The question is, will it be enough? It probably would be enough. I feel like I've done a demo like this before. And I think that it does attract, actually, if you put them close enough together, but you got to put them really close together. Okay, but the book says 3 is the right answer, right? Okay. I think this might be a situation where I think we should just try this ourselves, because maybe the book's full of shit. You know what I mean? It might just be wrong. So how about we say, Kavi, that we try A whenever we go into class, because we can reproduce this exact same experiment, okay? We totally can. So those of you that picked 1, we'll find out, okay? Sure, if I had you, okay. So we'll we'll try it. I would have chosen 3. I think it's the best answer, but I understand why you chose 1, and I was glad to see that not many, if anybody, picks 2. So you're all thinking the right thing. You're all thinking some polarization is going to occur. I like that. Okay, now what is different about part B? Now let's think about this. Part B says, now someone actually said what the answer was, and that's fine. I was going to wait to answer both of them, and then I was going to look the answers up. That's fine, but that's okay. Part B says, you now allow the spheres to touch. So now it's a different story. You allow them to touch. And the question is, once they have touched, will the two spheres attract each other, repel each other, exert no force? Go ahead and put your answer in the chat. Imagine you didn't know what the answer was. Yeah, Jasba, I think what you said is right. I think we're supposed to assume that they're far enough away that polarization's not happening. All right, everybody is saying that they will attract. Why will they attract? So we touch. What happens when we touch the spheres? So we bring the spheres together and we let them touch each other. What happens then?
The net negative sphere, well, the net negative sphere and the positive pole, I guess, essentially, of the other neutral sphere are attracting each other simultaneously. The negative sphere is repelling the other electrons of the neutral one to the other side of it, keeping the positive zone positive.
These are both insulators, right? So if I take an insulator that's negatively charged, it's got all these negative charges in it, right? Again, remember that when you have this is a conductor, right? If I have a conductor and it's got a bunch of negative charges in it, right? And I bring it next to a conductor that has basically neutral, so I'm not going to draw anything on it, right? If they actually make contact with each other, right? Well, now there's a pathway by which these negative charges can go fill in this new area, right? You know what I mean? They can flow, right? There's now a pathway by which the electrons can flow through here, flow right through this point where they're touching. And why would they flow? Well, they have to flow, right? Because if I'm an electron, right, and I'm sitting here, and I'm 100% free to move, right, and I'm surrounded by a bunch of negative electrons, I'm going to want to get away from them, aren't I? Because that's what negative charges do. So these negative charges will now start to funnel into this side over here. And so some of these negative charges now are going to fill up this other object. So I think that they will both, not only will they both become negatively charged, but I would go farther to say that if we started with a total charge on this object that was Q, that now what we're going to have is half of the charge is going to be on this one, and half of the charge is going to be on this one. That's what I think is going to happen. There's going to be an equilibrium that's going to be reached, where there's as many charges as can be in here will be in here, and as many charges as can be in here will be in here. And assuming that they're the same size, did it say anything? It says 2 lightweight metal spheres. Isn't this what's going to happen? Does that seem reasonable to you all? Yeah, and I agree with what Anna says. Yes. I agree with you, Anna. So, are you sure that's what the answer was? Whoever looked it up? Because I'm... Like, with the first one, I could see why 3 and 1 are both attractive answers, but this one, I really feel like this is the answer. How do we know, Jaspa? Well, I'll prove it to you later. But for now, just think about it like... imagine that each of these electrons is like a person at a party, and let's say you have a room in a party and everybody's stuck in that room, and they're all close together and they're like jammed in, and maybe a lot of these people don't like each other. So then as soon as you open a door and there's a pathway to get to another room, people are going to kind of spread out as much as they can. And when I say they don't like each other, well, electrons really don't like each other, right? They hate each other. They are constantly repelled from each other if they can. So they will get as far away from each other as they possibly can. In fact, they'll go all the way to the surface if they possibly can. And this is something we're going to learn more about later. I'm going to look up the answer now, because I'm confused. I'm totally confused. Which is fine, but... Alright, answers to quick quizzes. This is in... that's not the right textbook. So what section? This is quick quiz 2021.2. I think if we go to the very end, we can find the answers. Somewhere. Okay, it's probably easier to find if we do this. We go up to here, and we click on answers to odd number problems. 21. Okay, Anna says, yeah. Wait. Oh, okay, you guys that said attract were right then. So whoever said the answer was wrong. They looked at the wrong answer. Okay, you guys found it. And they say in part A it's attract, in part B it's repel. So I was wrong on the first one. I love it when I'm wrong. I love it when you guys are smarter than me. I think that's great. So these are the right answers. You guys were right. It is attract. It is attract. And the reason for the attraction is because, just as you said, you all were right, because of the induced polarization, right? I thought so. I thought you all were right because I was pretty sure that I'd done this before and I've seen it happen. So basically, part A, what's happening is that they attract because of the induced polarization. In part B, they repel each other because they both get the same charge when they touch. And then when you pull them back apart again, and you've got one object over here that's negative Q, and another object over here that's negative Q, well, now they obviously have to repel each other, right? So that's the answer. When the charge is balanced, right? The charge is balanced, but then you pull them back apart, and now you've got Q over 2. It's actually Q over 2. Q over 2. Okay, so 1 and 2, and I love it when I get these wrong. I love being made to be a fool. It's the best way to learn, you know? Is to think you know something and then have it be corrected. It's the best way to learn something. That's how everybody learns. That's how AI learns. Is you get it wrong and then you get corrected. So that's awesome. Okay, thank you so much, Kavi. I appreciate you asking this question. I really like these quick quizzes, and I like to filter them in from time to time, but I don't always do so. So thanks for bringing it up. Okay, is everybody clear on why those are the answers? Are we all in agreement? Part A, the answer was because of the induced polarization, they'll attract. And part B, the answer was 2 because they now have the same charge. Yep. Great question. These are the kind of questions you're going to see show up on like the multiple choice type questions that'll show up. Well, that one's pretty hard. Of course, now that we talked about it, we could easily throw it onto an exam. Okay, we have about 30 minutes left. So let's see if we can solve both these problems in 30 minutes. Now, I could do it, but I don't want to do it too fast. So what I'm going to do is I'm going to try to get it set up for you all, and then I'm going to have you all do some calculations, and then we'll try to solve the last problem too if we can. Okay. All right. So here's the next problem we want to do. You want to make no problem. Is that good? So this question asks, where is the net force 0? I believe you have a homework problem that is very similar to this, almost identical. Okay, we have 3 point charges. You're going to see that phrase show up a lot. A point charge is going to be an object that is effectively a point that has a charge, okay? Or just, kind of similar to a point mass from Physics 1A, if you remember that kind of stuff. So it says 3 point charges lie along the x-axis as shown in figure 23.8. The positive charge Q1, so Q1 is over here. We'll just look at the picture. We got Q2 right here. We got Q3 in the middle. Q2 is positive, Q1 is positive, and Q3 is negative. Okay. Unfortunately, I wish it didn't show these arrows because I wanted to ask you about those, but that's okay. The positive charge Q1 is 15 microcoulombs. Let's write that up here. Q1 is 15 microcoulombs, which is 10 to the negative 6 coulombs. And Q2 is 6 microcoulombs, so that's 6 times 10 to the minus 6 coulombs. Is at the origin. And the net force acting on Q3 is 0. What is the x-coordinate of Q3? So this problem is trying to figure out where does Q3 need to be, somewhere along the x-axis only. We're not going to move it up and down, although we could. Just be a little bit harder of a question. So we're looking for the place along here where the charge or where the force acting on Q3 is 0 due to the other two charges, right? So how can we figure this out? What can we do? What must be true in order for the force on Q3 to be equal to 0?
Forces at Q1 and Q2 cancel out?
Yeah, they should be both the same, right? So yeah, just what Josh had said there. So we know that we want to make it so that F23, which is we can read this as the force of object 2 on object 3, right? We want that to be equal and opposite to F13. Now, again, I wish these weren't on here, but would you all agree that if I put a negative charge inside of here, that the positive charge on the left is going to pull it to the left, and the positive charge on the right is going to pull it to the right? Does everyone agree with that? I mean, it's kind of just thrown on the picture, but... Okay. Now, which charge is bigger? Q2 is 6, right? And Q1 is 15 microcoulombs, right? And what's our formula? Well, our formula is the electric force formula, right? We got K, Q1, Q2 over R squared. So, or in our case, it's going to be like Q3, Q1. So let's write Q3 here or something like that. So yeah, so we need to make it so that these forces are equal to each other, just as you all said. And what should we do next? Should we think about what's happening with these distances? Should we just plug this formula here into this equation? What do you all think we should do? Should we work out the distances, or should we just plug this formula into this equation? You want to calculate the force for each. Okay. Now here's a problem with that. What's Q3 equal to? Do we know what Q3 is? It's not 0. It can't be 0. It needs to be negative, right? It needs to be a negative charge. If it was 0, then there would be no force at all. So we don't know what Q3 is, right? This isn't given. So, Kavi, we can't actually calculate the forces yet. We can't do it yet. But we could just take this definition of the force, right? And plug it into this equation and then just kind of see what happens, right? Like, not knowing if it's going to work or not, we could at least go to the next line, right? And then just kind of... That's right, Justin. Justin's thinking ahead. It does look like Q3 might cancel if we do that, right? Let's try it out. So F of 2 on 3. Right? Yeah, we can do a ratio too, Kavi. That works too. It'll work out to being exactly the same thing. What would the ratio need to be for this to be true? They'd be equal to... The ratio would be equal to 1, right, Kavi? So that works too. If you prefer to do that, you can do that. Yeah, go ahead and work on it. I mean, if you already know what to do, any of you that feel like you can already solve this, just go ahead and solve it. So what I'm going to do is on the left-hand side here, F23, we're going to go ahead and plug in our equation. So F23 is the force of 2 on 3. So what are the two objects involved? It's Q2 and Q3, right? So that's going to be K, Q1, Q3, and now I need to divide by the distance between them. Now, our goal in this problem is to find what the x-coordinate of Q3 is, right? So we're trying to solve for x. Now, this picture is really nice because they showed us that these two charges are 2 meters apart, that this thing is in the middle at a distance x away, and they even went so far as to tell us that this other distance is automatically going to be 2 minus x. And of course, by looking at this picture, that should all be pretty clear. But just keep in mind that you'd still need to figure this stuff out on your own if they didn't label that stuff, right? Anyway, so what we've done here is we've said the distance between Q2 and Q3 is just defined as x. So that's going to show up down here as x squared. Does anyone have any questions about the left-hand side of that equation? Does that make sense? The right-hand side of the equation is the force between 1 and 3, which is pushing to the right. And that force should be K. Oh, I'm so sorry. I'm so confusing. I'll put this in a different color so that it's clear. I made a mistake right here. That should have been a 2. So fix that if you were writing down notes or something like that. Because it's 2 and 3, right? Q2, Q3. The right-hand side, we're going to have 1, 3. So Q1 times Q3. And then we divide that by the distance between Q3 and Q1. And in this case, that's going to be 2 minus x. I'm going to write 2 meters minus x. So there we go. Just get a second to make sure everyone catches up. Does that make sense? Does anyone have any questions? why are we squaring the bottom? Good question. It's because that is how the electric force works. For electric force, what we do is you take K times one charge times the other charge, and then you have to divide by the distance between them squared. That's why. Yep, the distance squared. Yeah, it looks a little bit different when I don't put an R here, right? As soon as I put an X, it's like looks completely different. All right. So continuing along, as someone had already mentioned, we can now cancel out the Q3s. And we should have only one unknown now. What is our unknown? It's X. Yeah. So how about you all take your time and solve for X for me? In whatever way you prefer. Oh, something else canceled out too. We don't need to write the K's again. The K's cancel out too, right? Yep, we don't need to write that again. So we just get Q2 over X squared is equal to Q1 divided by 2 meters minus X. And that whole thing's squared again. So, yeah. Do you all want to solve for X, maybe? And again, don't put the answer in the chat until I ask, so that people have time to work it out themselves. I'll plug in numbers, too. As you're doing the calculation, just to make it a little simpler on you, you can cancel out these units too, micro and micro. Make the math a little easier. I very much want to do the other problems, so I'm just going to check. Did anyone get an answer yet? This math might take a little time, so I totally understand if you all didn't. Did you get an answer? Okay, so go ahead and put your answers in the chat if you had an answer. And then I really want to get to this next problem so that, that sounds like the right answer to me. I mean, it has to be less than 2. And it's a very, very round number. So I think that's the right answer. Did anybody else get the same answer? algebraically. Well, I mean, you can do it algebraically, but eventually you have to use the quadratic, you know. And of course, you can also just, you know, there's other ways to do it as well. Okay, let's work it out real quick. I can tell by the lack of answers that I know you didn't have enough time, but I want to reserve enough time to do this last problem and still give you time to think about it too, and not just blaze through it. So, what do we need to do here? What's the first step to kind of get x out of this? You know, how do I do it? How do I solve? It's the first step that you all took. Cross multiply. That's what I would do too. Yeah. So we're gonna get. Let's use a different color here. So we're gonna get 6 times. I'm gonna multiply this out. I hope that's not too confusing. So you're gonna get a 4 meters squared. You're gonna get a plus 2 times 2x. That's negative actually. You're gonna get negative 4x. You know what? We're dropping the units. It's too much. I can't write the units on this one now that we're gonna go into a quadratic. And then it's gonna be plus x squared. So here all I've done is just multiply out this binomial, square it. So you get 4, and then you get a negative 2x times 2, and then you get a positive x squared. And then on the right-hand side, we should have 15x squared. And then what we need to do is we need to basically just group terms, right? Combine like terms, yeah. So this is 24 minus 24x. I'm gonna, I'll do one more step. So then this is gonna be 6x squared. And then let's go up here. Nah, let's not, because then I'll run out of space because of the chat box. So our final result here is, let's move everything to the right-hand side. So we're gonna get 0 equals 15 minus 6 is 11. X, 24x right here. Plus 24x. Minus 24. And then that leads to x equal to, there's 2 different answers. One is going to be, I think it's a positive number. I can't remember if it's a negative number or a positive number. But one of them is definitely, do you remember what the other one you got was, Ton? Did you do both of the solutions, or did someone else do both of them? 9x squared. You know what? 15 minus 6 might just be 9x squared. You might be right there. Sorry about that. Alright. I saw 6 and 5 and I added them. And I got 11. I'm an idiot. Sorry about that. Alright, so you get 0.775 when you do this. We can throw it in the quadratic real quick right here. With, where's it? This one. Let's pull this up, and then we'll put this on top of it. Doesn't want me to do that. I have to go out of full screen mode, and then it'll let me. Okay. So that's our quadratic, and we just plug everything in. So it's going to be negative b, which is 24, plus or minus, we'll just do plus, square root b squared. What is b? 24. Is that the other answer you got? Was negative 3.4? Okay, 24 squared minus 4ac, 4 times 9 times negative 24, which is going to make this positive. We'll just put 24 right here. I'm sure I'll probably make a mistake doing this, but I'll do it anyway. Divide by 2a, which is going to be dividing by like that. And that's what you get. Ah, it worked. And then if we do the same thing, but we put the negative sign in here, I get the same answer you got. Great. So there we go. Yeah, how do we know it's not the negative number? Great question. How can we figure that out? How do we know it's not a negative number?
No such thing as negative distance.
Well, there is such thing as a negative x coordinate, though. And we're just finding an x coordinate, right? The 2 meter limit, maybe. Let's think about the physics. Well, I mean, yeah, you could say, oh, the pick, but, I mean, yeah. Yeah, that's a good answer, too. Let's think about this. So, 6 microcoulombs is smaller than 15 microcoulombs, right? Our answer said that the place where the force is 0, remember that's what we were doing, where is the net force 0? The answer is right here, 0.775 meters. Sorry, I should have put a unit on here. Why is it the case that the answer we got is closer to the smaller charge? Why did it have to be the case that our answer was closer to the smaller charge? Why was it the case that you need to be closer to the small charge so that the force is balanced to 0? Because that's what we're trying to do. We want the forces to balance to 0, right? So why would it be the case that when you get closer to the small charge, that would be the place where that would happen? No, it's not because of the diagram. To make up for the other charge, what do you mean, Evan? Distance is inversely proportional, right? That's exactly right, Gavi. So that means that you can look at the equations right here. Q2 is inherently smaller than Q1, right? So that means that this denominator here has to be smaller than this denominator, right? I don't know if that makes any sense, but this number needs to be small to make up for the fact that this is small, so that you can counterbalance the fact that Q1 is big, and then this will correspondingly be bigger. Okay. All right. Now, how do we know it? Did that make sense to you all? It's because, I mean, the best answer is what Kavi said. Distance inversely proportional. That means that the closer you get to the 6 microcoulomb charge, the bigger the force you're going to feel from that 6 microcoulomb charge relative to the 15, which is farther away. Yes, I mean, Mendoza, that's exactly right. Yeah. Because Q1 is big, Q2 is small, Q2 has to be closer. You have to be closer in order to make it so that this force is as big as this force. We can go to an extreme, right? Suppose that we change this, instead of 15 microcoulombs, we make it 150 microcoulombs. Well, certainly if there's a 150 microcoulomb force over here and a 6 microcoulomb force over here, you're going to have to be really close to the 6 microcoulomb charge in order for it to produce enough force to counterbalance the force from something that's so big over here. Because the closer they get, the bigger the force is going to be. Okay, let's answer the second part. How do we know it's not the negative answer? Because we got or negative 3 something, right? Negative 3.44. Negative 3 point. We'll call it 3.4. How do I know that I can X that one out? Well, let's draw a picture, okay? Let's draw a picture. So, if I put a positive charge here, right, and I put another positive charge here, negative 3.4 means that I would put my negative charge, well, where would I put it? I'd put it way back here, right? That's where Q3 would be. So this would be Q3, sorry, Q2, yeah, 3. This would be 3, this would be Q2, and this would be our Q1, right? Now, let's think about the direction of the forces acting on Q3. What's the direction? First of all, for Q2, what's the direction of F23 now? Is it going to go to the left or is it going to go to the right?
The right.
To the right, right? Okay, so this is the force of 2 on 3, right? So just like they did in the picture, I'm going to call it F23. What about 1? What's the force of 1 on 3? What direction is that going to point? The right or the left? To the right, okay. And which one is, now here's another question. Which one is going to be bigger? The force of 2 on 3 or the force of 1 on 3?
2 on 3?
I actually think they're going to be equal to each other, and I'll tell you why in a second. Nah, there's no way they're, maybe they are. I don't know. You could at least conceive that they would be equal to each other though, right? You can conceive that they'd be equal to each other, because remember, Q1 is bigger than Q2, right? Even though Q2 is closer. And after all, this is the answer to the question, right? Remember, this is a math problem. At this point, it's a math problem, right? This is an answer to a question, what values of x solve this problem, right? So, when I plug in negative 3.4 into this equation right here, it 100% makes these two things equal to each other, right? Would you all agree? They're equal to each other, right? Is the force 0, though? Is the net force 0? No. Why not? Yeah, it's not 0. Why not? Because they're going in the same direction. The net force is now double that, right? So that's the physical reason why you have to get rid of this. Does that make sense to everybody? It's because if you were to place the object there, you would still meet the... Remember, this was our original... We didn't say that one has to point left and one has to point right. We just said they have to be equal, they have to be numerically equal to each other, right? They have to be numerically equal to each other. That's all we said. And the math worked out that you get two answers. It always will, if there's two solutions in a case like this, because it's a squared situation. So, yeah, I mean, it gave us an answer that's real. It's a real answer. It's a place where the forces are equal to each other, but not in opposite directions, because this equation has no idea of what's going on with the vectors. It's not a vector equation. All right. So, 4:11. We had 9 minutes. There's no way. Can I just do this problem, and then maybe next time we come back and we just start with it or something? I want to at least talk about the idea. I want to at the very least talk about the idea of what's going on here, because it's yeah, the layout. What is the layout? All right. Yeah, the layout of the problem. Yeah, that's what we'll do. We don't need to solve it. We'll set it up. That works fine, right? Okay. Consider 3-point charges located at the corners of a right triangle as shown in the figure, where Q1 is equal to Q3 is equal to 5 microcoulombs, and Q2 is equal to negative 2 microcoulombs, and A is equal to 0.1 meters. We want to find the resultant force exerted on Q3. So now this is where we did something in the last problem that was related to this, but now it's worth talking about superposition of forces. This isn't a new concept. It's something that you use in Physics 1A, but I want to kind of reiterate what it is. When I have multiple forces acting on an object, right, if I want to find the net force, then all I have to do is to vector sum all of the forces individually acting on it, okay? In this particular problem, it's asking us, if I have a negative charge here, a positive charge here, and a positive charge here, it's asking us, what is the net force on this Q3 right here? And for superposition of forces, the idea is, if I find the force of Q1 on Q3, which is going to be a vector, you all tell me, what direction does it point? If I want to find the force of Q1 on 3, the force on 3, what direction is that force going to point at this location? I'll give you two options. It's going to point northeast, or is it going to point southwest?
Northeast.
Northeast. Northeast, right? Okay. So let's draw our vector. And let's label it. This is going to be the force of 1 on 3. And yeah, can I just call it F1? Are you okay with that? It's a vector, F1. Okay, let's go to the next one, Q2. Again, we're finding the result. You gotta be careful about the way this stuff is worded, because it will be very confusing to you, for sure, the first few times you do this stuff. The resultant force on Q3. So in order to find the force on Q3, I need to add up all the forces acting on Q3. One of them is this one. The other one is Q2. So type in the chat what you think the answer is here. Is the force of Q2 on Q3, okay, the force on Q3, should I draw a vector to the left or the right? Type your answer in the chat. Left or right for the force? Yeah, left. That's right. Okay, let's put that on here. We'll make it blue. Blue. Shapes. Click. All right, so those are our forces. I did not draw these to scale. Just for kind of running out of time. So that's F2. Now, superposition of forces, the idea is that if I want to find the net force acting on an object, well, all I have to do is sum up all the forces, right? You would take F1 plus F2 plus how many ever you have. Okay, that's how we find the net force acting on Q3, is we have to vector sum F1 and F2. That's basically all we have to do. Of course, how do we add vectors? We usually break them up into components and then add them, right? All right. Well, let's see how much of this we can get through now. Probably get through quite a bit of it, actually. So, yep, we can put them tip to tail. That's another way to do it. That's right. So what I could do is I could put this one here, right? If they were drawn to scale, and then that would give us an idea of what the direction of this net force is going to be. We can tell them that the net force would be a line that would kind of point up that way. So this is where we can do what I think it was Kavi had suggested in the last problem, which is where we can actually just calculate what F1 and F2 are now, right? In terms of magnitudes, F1 is just equal to K, Q1, Q2, divided by the distance between them squared. What's the distance between Q1 and Q2 here? It's this, square root of 2a. So we'll just plug in here square root of 2a, and then we have to square the entire thing. That's what F1 is. F2, leaving a little space. Again, I'm just doing magnitude right now. F2 magnitude is going to be equal to K, Q... Okay. I gotta stop making these sloppy mistakes. This should be Q1, Q3. Yeah. Q1, Q3. That's what F1 is, right? Sorry, Mendoza, my bad. F2, this should have been a 3 right here. I just changed that to a 3. All right, F2 should be 2, 1, 3, right? So it's Q2, Q3, divided by this distance, which is A, and A is squared. Now, we know what all these values are. We know that A is equal to 0.1 meters. We know, well, you can see up here what all the rest of them are. All right, here, so it's bigger. Q1 is 5 microcoulomb. Q3 is also 5 microcoulomb. And Q2 is negative 2 microcoulomb. So now what we can do is we can just straight up calculate these things. In the interest of saving time, I am just going to plug these numbers in, and you can see what they all are here. And we're just going to get an answer, just in the interest of saving time and trying to get to the next part, which is the part that's different now. So we've got, all right, so K, 9E9. Q1 is 5 microcoulombs, right? So that's times 5, E minus 6, times Q3 is Q3 is also 5, so 5 E minus 6. And we have to divide by the square root of 2a squared. Well, the square root of 2 squared is just 2. And then we're dividing by a squared, and a is 0.1, so we got to square that. That's what I got, 11.25. We'll write that down in a second. And then we need to do the same thing, except all we have to change is the distances. So there's no 2, and we need to change the charges because it's 2 and 5 now. So change that to a 2, and we get 9. So it's 11.25 and 9. This is 9. That's what you got to learn, Haiti. You got to learn how to know what directions these point, and it's based off of, all it's based off of, Haiti, is opposite charges repel. Sorry, opposite charges attract, and like charges repel, right? That's all that is. That's where I got those from, okay? All right, so F1 is 11.25, F2 is 9. How do I add these together? In 1 minute. You got to find components, right? So what you do is you come up here and you break your force into components. I would normally do this using vectors, just running out of time. So we're going to have some angle right here. And I'm going to say that this piece right here is F1 cos theta. Does that seem familiar to you all? Do you all remember this? If I say that's F1 cos theta, you remember that? F1 sin theta, you remember the trig? Great. Now what we can do is we can say, well, the total force acting on this object, if I want to sum up these forces, what I can do is I can take these two because they point in a line, and that'll give me my x component, and this will give me my y component. So I'm going to say that if I sum up all the forces acting in the x direction on this object, what I'm going to get is F1 cos theta minus F2. And if I sum up all the forces acting in the y direction, I'm going to get just F1 sin theta. What is theta? In this case, we have a triangle that is A by A, which means that this angle theta is equal to 45 degrees. That also means F1 cos theta and F1 sin theta will be the same number. That being said, we can go ahead and plug them in. So we'll have Fx is going to be, F1 is 11.25 newtons times the cosine of 45 minus F2, which is 9 newtons. Now this should give us a negative number if we did it right. If you all can calculate that for me, that would really help. And then over here, the net forces in the y direction is going to be equal to F1 sine theta, so that's going to be 11.25 newtons multiplied by the sine of 45 degrees. Multiplying those out, we get an x and a y, fx and fy. The first one you're saying you got negative 1.05 newtons, and the second one, what do we get? 7.95. Those answers sound correct to me. In fact, we can check very quickly that if we approximate that this first number is about 8, which it is, if we take 8 minus 9, you get 1, negative 1. So that's good. So that is our answer, and what we can do is we can write this in vector form by saying that the net force is going to be equal to negative 1.05 I hat plus 7.95 j hat, and these are in newtons. And that is all we have time for today. I will stick around and be happy to answer any questions that you have. Apologize that we went through that so quickly, but trust me, we're going to see more stuff like this, and I think it's a good idea to at least have a fully worked problem. You can always go back, and when I post it on YouTube, you can go back and watch it a little more slowly. So sorry for going through a little fast there, but I think we talked about some good things today, and I hope that you feel like you can go home and kind of try this homework out. It's currently due Monday, but I'm going to shift all the homeworks by a week just because of this Labor Day thing. And you should be able to do a lot of it, but there are definitely going to be problems that are going to be really hard. For those, you can read the textbook and it'll help you out with them. Next lecture, next Wednesday, is going to be very challenging, I'm just going to say. Because what we're going to be doing, just as a preview, is we're going to start looking, first of all, we're going to define something called the electric field, and then we're going to spend an entire class working out the electric field of different charge distributions. So what we're going to do is we're going to look at like a rod that's full of charges, and we're going to do something similar to what we just did now, but it's going to be a uniform rod with charges uniformly distributed throughout it, and it's going to require that we do some integrals in order to do the electric field calculation. I would highly, highly, highly recommend that you finish reading chapter 21, okay? No lecture Monday. We will meet on Discord next Wednesday, absolutely. We will start the first lab a week after that. But just to reiterate, please, 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 before next Wednesday, we have a week, right? We have a week. Homework would be the Mastering Physics on Pearson, yes. We have a week. Please read the section in chapter 21 about continuous charge distributions. It will immensely help you if you have covered this topic before you come to class, because it is incredibly difficult. I remember when I first took this class that I watched the professor do this stuff. I went home and I was like, I'm going to do these homework problems. And then I tried to, and it was straight up impossible because I just didn't put the time in. So it's right here. It's the section called electric field calculations. Now, we'll be doing that problem, and then we're going to be doing these problems. These problems here, 21.9 and especially 21.10. If you can only read one of these problems before you come to class, okay? Example 21.10 in the textbook, the field of a charged line segment. This is very challenging stuff. You will have to do it on your homework. It will show up on your lab manual problems. It will show up on exams. Please read it before you come to class next time, okay? That's my only expectation. I'm sorry for keeping you late. I'm sure you all have classes to go to, so I will stop there. But thanks for sticking around. And thanks for coming today. And thanks for all the good questions. Thanks for being involved. I'm really enjoying that. So, have a nice day, you guys. Yeah, thank you. Have a nice day. Let me...
Professor?
Yes.